Hello and welcome to the first video on differentiation. After all that long introduction on limits, we are finally ready to get down to business. So let's waste no time. Now, if you look at the notes on the first page, you see calculus, intro to differentiation. First of all, what is calculus? So calculus is a big umbrella. Underneath it, we have two main topics. Number one is differentiation, what we're going through today. Number two is integration, something we'll be learning down the road in a few months' time. So then what is differentiation? So differentiation is about finding the gradient of a graph. And sometimes graphs are not as straightforward as a straight line. A straight line graph is easy to find the gradient. But what if we have a curve? Yeah, how do we then find the gradient of a graph at different points of the curve? So that's what differentiation is about. So I'm going to go ahead and check the first checkbox off. That is calculus, that is differentiation. Next, who are these two dudes and why do they have long hair? Well, it shows what era they come from the 1700s to 1800s. Right, the guy on the left, very famous, apple drops on his head, that is Sir Isaac Newton. And the one on the right, lesser known but still quite famous, Gottfried Wilhelm Leibniz. And the two of them are given the major credit for discovering calculus. Okay, here's a little gossip on the two of them. They did not get along. Both of them were trying to make claims as to who was the first to discover calculus. So, although Sir Isaac Newton is a genius through and through, right? I felt he was a bit petty in the dispute between the two of them. At the time when they were disputing, Sir Isaac Newton is a very famous and influential figure, and he had his ways and he managed to convince his contemporaries that he was the first to discover calculus. But as you see today, we credit both of them, not just Sir Isaac Newton. That is because Leibniz has also made a very significant contribution. And we're going to learn about what he contributed rather soon. Okay, so those are the two people, Newton and Leibniz, who discovered calculus. So next, I'm going to have a quick recap and review on gradient. How do we find gradient, say, of straight line graphs? And that is through this thing that we call rise over run. So what is rise over run? Might be the first time you're hearing this. So if I have a graph, for example, say a green straight line here. Yeah, not a very straight line, I'm sorry. Okay, what if I wanted to find out how steep or how gentle this green line is? I can give it to you. I can determine it mathematically. I can put a number to how steep it is. That's very simple. Oops, sorry. Right, we pick 2 points first of all. Say I pick 1 point here, and then I pick another point here. Okay, and then what I want to do is measure a change in the vertical distance, which we call the rise, because like how the sun rises, it will become higher, or if the sun de-rises, it will actually go down. Yeah, I know it's called a sunset. Yeah. Okay, and then the other thing that we're interested in is the change in horizontal distance. That is the run. So if you find the change in vertical distance and you divide it by the change in horizontal distance, what you get then is the gradient, a numerical number that tells you how steep or how gentle a line is. Okay, and some of you might know this as a formula, which is y2 minus y1 over x2 minus x1, right? So for example, say the point over here has a coordinate of x2, y2, and the other coordinate here is x1 and y1. Okay, so you can see very clearly that y2 minus y1 is nothing but the rise. Yeah, y2 minus y1 is the change in the vertical distance, and then x2 minus x1 is the change in the horizontal distance. So what you learn is no different from rise over run. Okay, so that was a very, very quick recap. So if you're still not sure on this, you need to go and revise your straight line graphs. Very important before you start on differentiation. Okay, so again, I'm going to go ahead and check that off. Next, let's put ourselves in the shoes of Sir Isaac Newton, right? What else could he be thinking about as the apple drops on his head? So instead of having the apple drop on our head, maybe we can consider an apple dropping to the ground. And let's say the apple was 2 meters off the ground, and then it took 1 second to hit the ground. Does it actually mean that the speed of the apple is 2 meters per second all throughout its trajectory, all throughout its fall towards the ground? So that's an interesting question we want to discuss. And to convince you, right, I'm going to show you a YouTube video of a physics teacher conducting an experiment. So this experiment is rather simple. What this teacher is going to do is going to drop a golf ball 1 meter off the table. You can see the teacher is holding the golf ball pretty high up. That is, in the other hand, he's holding a meter rule. Okay, and he's going to drop the ball, and they're going to use slow-mo to show you very slowly how the ball drops. So pay attention. He's going to drop the ball somewhere around 1 minute 36.2. There you go. Okay, so I hope you caught that, because the thing that you should be watching out for, let me rewind it again in case you didn't catch it. The thing that you should be watching out for is the ball traveling at a constant speed. Yeah, so you can use the meter rule to help you gauge, right, how far is the distance traveled as the ball drops. Yeah, so hopefully you caught that, and you can see that the speed of the ball is not the same throughout this journey. Okay, so what that means is, okay, if I drew a distance time graph instead of a speed time graph, a straight line will not be a good approximation of the trajectory of how the ball or the apple falls towards the ground. Because if I have a straight line over here, it means that the speed is constant. Yes, the speed is constant, the gradient is constant. That is not the case, right? What is actually happening, I suppose, is this. This is a better approximation of the trajectory of the golf ball or the apple. It looks more like this. And let me convince you why this is the correct shape of the trajectory. What I'm going to do is I'm going to split the 1 second up into 4 portions, into quarters, right? And what we can do is we can take a look at the distance traveled in each quarter. So in the first quarter, from 0 to 0.25 seconds, this was the distance traveled by the apple or the golf ball. Okay, and you can see the distance is not much. That is because at the moment where the apple or when the golf ball is released, right, the speed is actually 0. It's actually 0. Yes? So it is slowly picking up speed from 0 and it's increasing in speed as it falls down. So since there's a very, very low speed at the start, it did not travel much in the first quarter. So in the second quarter, this is how much it traveled. Yeah, this distance over here. A little bit more than the first quarter, yeah, but still not much because the speed is still increasing. Now, if you look at the third quarter, that's when you have quite a big increase in the distance traveled because the ball is picking up speed. And finally, in the last quarter, right, you have another big increase over here. Okay, so this is then a better approximation of the trajectory of the apple, of the golf ball. But that will also mean that our gradient is changing all the time. It's no longer constant. Okay, and I think that's a very interesting question, because what if I wanted to find out, say, the speed of the apple at this point in time? Yes, just this point in the green spot here. What is the speed over here? What if I took a snapshot, I took a picture of the apple at this point in time and I show you the photo? Will you then be able to tell me the speed? Yeah, that is an interesting question that we're going to talk about in the next video. So thank you for watching, and I hope to see you in the next video. So catch you on the flip flop.